Hello there, and welcome to why you should care about topological fusion for computer vision. The motivation for this work is that computer vision models have become huge over the past years. Huge could mean a lot of things. Large numbers of parameters, millions, billions even, alongside which comes huge training time and large requirements on the compute resources necessary to train, which of course in turn results in environmental impacts and a whole bunch of other things. This is an old story, we've heard this before. What can we do about it? More specifically, how can we retain the same good performance that we like about these big models with much smaller ones? One idea is to leverage powerful mathematical tools in order to help neural networks out, sort of make their jobs easier, if you will. One promising direction along these lines is a technique called topological data analysis, or TDA for short. TDA aims to provide rich structural information about many types of data, including images. And it comes with some pretty nice perks. It's resistant to noise, and evidence suggests that neural networks don't learn these types of information by themselves, which makes it a logical thing to include in a fusion model in order to save on parameters. So that sounds great and all, but what's the catch? Why isn't everyone doing this? Well, unfortunately, TDA can miss out on many important features in naturally occurring images, the types of images that we care about in computer vision. And this results in it lacking the specificity required to be very useful for deep learning. And this is an important problem which needs to be addressed in order to fully leverage the power of this type of information. So let's try and fix it. The problem arises in images that have large sections of either dark or light pixels. You can think of things like a dark background or a patch of sky, things like that. Very common types of features we see in almost any image in a computer vision dataset. The reason this causes problems for normal TDA is that it relies on intensity thresholds in order to compute the topological features. By switching these over to intensity bandwidths, we can get around this problem completely. The only catch is we'll need to tweak the math a little bit, but that's not a big deal. So let's take a look at what this actually looks like. Over here we have a few images. In the upper right, we have the original picture from which everything else was generated. And immediately below it, we have the results of running some TDA. Or more specifically, we have the subsets of the pixels that are used to compute the topological features. As I increase the filtration parameter, which in this case is just a simple grayscale intensity threshold, what starts happening is that the shadow of this plane, in this case, starts eating up everything else in the image, which results in a lot of important aspects of the image not being captured because they got eaten up by this big component. If we now turn our attention to the other 8 images on the main part of the screen right now, we can take a look at what happens when we do this with bandwidths instead. This is just a subset of what is extracted with the proposed method, but already you can see that we can extract many different kinds of features that were previously very difficult to obtain with normal TDA. And if you're curious, this is what it looks like when you throw all the features from this new technique into a big graph and stare at it. That's all fine and good, but what does this actually mean for the real world? This slide should convince you that there's a clear reason to incorporate these features into deep learning models. We have a couple different experiments here. based on some different models, and you can see that with the proposed method, we can very effectively outperform not only models of the same size, but models that are considerably larger, simply by adding in some of these features. And that is why you should care about topological fusion.